All right, here we go. Question number 6 is drawing all the lines of symmetry in the following shapes. Well, I'm going to assume, I know I shouldn't, but I'm going to assume that that's an equilateral triangle. And if so, I'm going to have some symmetry. And if I turn it sideways, I can be like, okay. And then if I go that way, I can do it like that. So there's actually 3 lines of symmetry that I could fold the shape over, and it would, be symmetrical. It would be congruent on both sides. Now I'm going to assume this is a square, because if this is a square, then it should have 4. 1. So you can imagine I can do a better job. Imagine folding it across the y-axis, see its symmetry. Or imagine folding it across its x-axis, and you'd see its symmetry. But we'd also have these diagonals that we could fold only if it's actually a square. If it's a rectangle, that's not going to work out for us. All right, and then lastly, we got this isosceles because it has 2 congruent sides, and it only has symmetry through the y-axis. All right, so if I folded it over, bloop, that point would fold over to that other side, and it would match perfectly. But that's the only symmetry that shape has. Cool. So that was lines of symmetry, and the next one we have rotational symmetry. I was thinking about this in my yard. I have a bunch of these little pinwheels in my yard to keep hawks away from my chickens. This pinwheel has a 1, a 2, a 3, a 4 little spinny wing things. So it has a rotational symmetry, which means it'll look just like it looks right now if it rotates how many degrees. And we can figure out that number because a full rotation is 360 degrees, and there's 4 matching parts, so we'll do 360 divided by 4. Every 90 degrees, that thing will look like itself. In my yard, the pinwheels have 7 little spinny wheel, wingy, reflecty things. So in my yard, those things would have a rotational symmetry of 360 divided by 7, which I'm sure is a number. While we're talking about rotational symmetry, if I looked at this triangle's rotational symmetry, because it has 3 matching parts, it would have rotational symmetry of 360 divided by 3, 120 degrees. So every 120 degrees, the orientation of this thing will look like itself again. Cool. This square has 4 matching parts, so its rotational symmetry should be 360 divided by 4, which is just like the pinwheel. Hey, best friends. And then this guy, because it only has 1 long side, it would have to rotate a whole 360 degrees to get back to itself. So we say that it does not have rotational symmetry. So if it's 360, that's not rotational. All right, let's move on. On the next one, it says select all the transformations that are congruence transformations. So congruence transformations, we've been calling those rigid motions. But what that means is it just keeps its congruence. It stays the same size. It stays the same shape. So our congruence transformations include and only include translations, reflections, and rotations. Those 3 are congruence transformations. The one that's not is a dilation. We call that a symmetry. Words is hard. Not symmetry, similarity transformation. Okay, we call that a similarity. Okay, which means it has the same shape, but it changes its size. It's either an enlargement or a reduction. So what we're trying to do here is pick out the ones that are congruence transformations only. Well, this little r stands for a reflection. So little r for reflection. So yeah, that's totally going to be a rigid motion or a congruence transformation. Translation, yup. Dilation, nope, that's a similarity transformation. A big R stands for a rotation. So yeah, that works because it's the same size and shape. Plus, it's just one of those three. This is a translation. We see the translation rule. So yes, that's a rigid motion or congruence. This one's a no. It's a dilation. Okay, with a k equal to 2. So that's a dilation with an enlargement of 2. And then here's another translation. So yeah, that's a congruence transformation. So they're trying to trick you here by giving you different notations. Okay, here we saw the notation for our reflection, the notation for our rotation, translation rule, translation vector component, and this one gave you a dilation rule. So they were trying to be sneaky on some of those. Don't get tricked. All right, the next one says identify the congruent figures. So I'm going to start with JHK, and I see that it was rotated to form QRS. Now, when I say this, I got to be specific on who matches what. So I'll be like, all right, JHK is congruent to, and then I got to say what point matches J. So you need to know that after a rotation of 90 degrees clockwise or 270 counterclockwise, J would line up with R. H would match up with Q, and K would match up with S. So the order matters. J had to match up with R, H with Q, and K with S. Order matters. All right, now this one, we got a rectangle M in PL. And that looks like it was just slid down and over. All right, so that would be congruent to, and the order matters. So what matches with M? E. What matches with N? F. What matches with P? G. And what matches with L? That's D. So order does matter. All right, and then lastly, I have what looks to be a reflection. So C is 1 unit away from the line. So C matches with T. A is 1, 2, 3, 4, 5 units. So it should match with 1, 2, 3, 4. That matches with V. So A matches with V. And then lastly, B is 1, 2, 3, 4 units away. And U is 1, 2, 3. Uh-oh. They don't match. B did not match with U because B was 4 units away from the line and U was 3 units away from the line. So that means it wasn't a good reflection. It looked like it was going to be a reflection, but it wasn't because they didn't do it right or something, whatever. It doesn't line up. It doesn't work out. So the two congruent ones would be these guys, and then this one would not be congruent. Honestly, you could tell just by looking at it. This had a base of 1, 2, 3, 4. And this had a base of 1, 2. Well, they both had a base of 4. This one went up 1 and over, up 2 and over 1 to get to B. And this went up 2 and over 2. So if you looked at it closely, you could tell that they weren't congruent. This revolving door is divided equally into 3 parts. At what angle of rotation will you exit the building if you enter the revolving door from the... Oh, that looks like fun. Okay, so there's the right answer, and then there's the answer I think is more right. It says it's divided into 3 parts. So I'm thinking they want to talk about rotational symmetry and stuff. Probably. I would argue on this question because look at the way the door is shaped. The door is shaped like that. Okay? Yeah, the thing moves around on the inside, but really go out 180 degrees what you came in. So I'm going to argue that question. I think it's something to do with rotational symmetry. So I'm thinking they're wanting you to do 360 and it's divided into 3 parts. I think that's what they want you to do, but not sure if I'm buying it. Okay. So the answer that they probably want is a rotation of 360 degrees. It's got 3 parts. It's 120 degrees. But if you look at this door, you're kind of going out the other side. So I'm going to argue that it might be 180 degrees. You know, what about those people that just want to stay in it and keep going around in circles? Whatever. Moving on, describe the similarity transformation. So what did I do? How did I dilate? Let's see. Remember, start at the one that does not have the primes. We're going PQRS. So start at PQRS. Well, it looks like the first thing it did was reflected. So the first thing we did was a reflection over the, looks like the y-axis. So we started with a reflection over the y-axis. All right, so now I'm at this red guy with the primes. Hi. Now, how did I go from that to this little green guy? That's the question. How did I get to W, X, Y, Z? So it was definitely dilated, but how much was it dilated? So to figure that out, we've got to figure out what K is, which is what we had the hardest time with. Remember, the K is found by doing the image over the pre-image. So where did you end up? We ended up with this little green guy, okay? And the little green guy, I'm just going to count the easiest side. The little green guy, the bottom side, YZ, is 2. So one of the sides on the image, the last thing that I get to, has a side length of 2. Okay? The matching side on the one I started with was 1, 2, 3, 4, 5, 6. So it was originally 6 and went from a 6 to a 2. So we would say its scale factor, K, was 2 over 6, which can be reduced to 1 over 3. So that means our first thing we did was a reflection, blah, 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 we got that. But after that, we shrunk it down from 6 to 2. Shrinking it from 6 to 2, we did the math here, means we had a scale factor of 1/3. Which means my dilation rule is going to say, well, it had a scale factor of 1/3, so it was 1/3 X, comma 1/3 Y. Done. That's it. All right, next. All right, given the dilation, answer the following. Okay, what is the center of dilation? Well, that was point C. Is it an enlargement or reduction? Well, let's start by finding K. Remember, K is image over pre-image. So that's going to be the one with the primes, which has a length of 24, over the one with not primes, which is 9. 24 over 9. I think this one was taken straight out of your book. You can reduce that by a factor of 3, so it'd be 8 over 3. So the scale factor K is 8/3, and is 8 over 3 bigger than 1? Well, is 8 divided by 3 bigger than 1? Yes. So because K is bigger than 1, it's an enlargement. So K is bigger than 1, it's an enlargement. Whoop, whoop. Well, I guess I'm supposed to put B there. All right, almost to the end. The original photo measures 2 inches by 3 inches. That's the one on the left. So 2 inches by 3 inches, and that's the original photo. We'll give it a P for photo. All right, we have a new bigger one, P prime, with a dilation of 2. Scale factor is 2. So that means my K is equal to 2. So you guys should know exactly what to do. You'll take that 3, multiply it by 2. So that's going to be 6 inches. You'll take that 2, multiply it by 2. That's going to be 4 inches. Okay, so we have 4 by 6. 4 inches by 6 inches. All right, if 4 of the smaller photos can be printed on a single sheet of 4 by 6, how many of the large photos can be printed on the same size paper? Well, the answer is obviously 1, right? It's 4 by 6. Our picture's 4 by 6. It's 1. All right, and then last up, which of the following scale factors would produce a segment shorter than AB? So shorter means it needs to be a reduction, which means k needs to be less than 1. So we need all the numbers that are less than 1. Is 1/3 less than 1? Yes. Is 3 less than 1? Nope. Is 4 divided by 5 less than 1? Yes. Is 5 divided by 4 less than 1? No, it's 1.25. 7 divided by 2? That's 3.5. 1? No, it's exactly 1. And then 1/2 is less than 1. So we were looking for the numbers that were less than 1.